This is just a simple picture we took off Flickr, and then we've inserted this glowing sphere into the picture, moving around, and it looks like it's actually a part of the scene, or at least it does a reasonably good job of that.
Welcome to the Full Spectrum. Today we're talking with Kevin Karsch, a PhD student who researches computer graphics and computer vision. Welcome, Kevin.
Thank you. Thanks for having me.
So this photo is just a picture of someone's room, right? With no light in it, and then this is a digitally generated object that you've thrown in here, and it's casting light under the table, all around everything. Is that right?
Correct. Yeah, there's nothing else, no other information but from the picture that we have here. And so the user's given us some information, which we'll get to later. But yeah, this is just a simple low dynamic range picture that we took off Flickr.
So talk a little bit about how what you're doing is a little different than just, grabbing, in Photoshop, the outline of, me and sticking me in that scene.
Right. So if you're going to do that in Photoshop, just take one clipping of a picture and insert it in another picture. You don't know the perspective, so you don't know the focal length that the pictures were taken at. You don't know how large the objects are. You don't know the geometry of the object if you want to incorporate shadows or lighting information. And the biggest issue is you're just manipulating pixels if you're doing this in Photoshop. And so if you're using some type of 3D representation, then you're actually manipulating objects in 3D and then rendering that onto the image plane. And so the pixel manipulation is done by the rendering software rather than you explicitly changing the values of the pixels. So in that sense, it's much harder to do it from just a 2D pixel manipulation standpoint. And so again, the shadow here casted onto the wall, if trying to do this without the 3D model would be very difficult. You might be able to fool people, but to actually get it physically correct would be a challenge. And getting effects like this, especially things like caustics and proper shadows, there were some caustics on the table and some complex shadows from that. It's a heptoroid in the front, the black thing, would be very difficult to achieve using Photoshop. So if you took the statue in the back, and you just took it from a different picture, the specular highlights that are on the stomach and the face and the arms would likely be different if it was taken out of a different picture. And if you wanted to insert it here, you'd have to try and remove those specular highlights and change them so they match the scene. I mean, you wouldn't have to, but if you wanted to make it look realistic, you'd have to do things like that. This is another example where there's caustics coming from the sun flecking onto the snow. So if you were to take a picture of the scene with that 3D object actually in the picture, and then take one without the statue there, the amount of light coming into the camera would be different depending on whether the object was in the scene or not. And this actually occurs naturally within our method. So when the object's inserted, the scene becomes visibly darker because the amount of light coming to the camera is different.
Why do we want better techniques to put synthetic objects into a photograph?
Well, there's been a lot of work on this in the past. Most notably is Debevic's light probe method, and most of the time when you see computer graphics composited into movies or any type of video or even still images, I believe that the HDR probe method is what's usually used. It works really well, first of all, but the biggest problem is that you have to be able to go back to the scene and take a picture of this mirrored sphere, which gives you lighting information from all angles of the scene, so you can insert a synthetic object at that position in the scene. And depending on your skill level, it might take you some time to take these pictures and create the environment map, which comes from the HDR light probe.
How do you actually give your system the information it needs to make these possible?
The main idea is we want to take our picture and we want to get a 3D model of the scene from our picture. So here what you're seeing is our geometry estimation stage. We first apply an automatic estimation procedure which tries to find the boundaries of the scene. So it tries to find the walls, the ceiling, the floor. And then sometimes this is inaccurate, and we have an interface that allows the user to manually refine this estimate. By making a couple assumptions with 2 vanishing points, we can recover the focal length of the camera, and then using the rest of the input, we can also recover the 3D geometry, or a rough representation of the 3D geometry of the scene, where the floor is at, where the walls are at, and where the ceiling's at. So the next part after the geometry stage is our lighting stage, and the user gives us, they say where the lights are at in the scene by clicking in the image. So here we say that, or the user is indicating that there's one light source and it's coming from the window, and the light source is shaped like this, and the polygon defines the shape. And based on our camera parameters and the 3D position of the wall, clicking in the image, we can project that click onto the 3D geometry. And then we know the position of this light source in 3D, and we just assume it's a planar area source that's lying on the wall. Yeah, so this is the occluding object stage. So by scribbling in the image here, we can use the spectral matting procedure to get an object mask, and these object masks are then applied so that inserted objects are behind the masked objects. Yeah, so this is using our, we call them supporting surfaces. So they support insert geometry. So these are usually things like tabletops or couches or chairs where you can insert objects on top of. So by just using 2 of these supporting surfaces, one for the gutters and then one for the surface of the pool table, we can extrude these out from the floor. So they're just extruded polygons from the floor, and then we can just insert these objects into that on top of the table, and then by applying some physics, which is available in most 3D modeling packages, we can have them bounce off the gutters and make it look like there's actually a pool game going on. We don't actually have where the pool balls can go in. Like, we haven't modeled that, so it wouldn't actually, if they were going to go in one of the holes, then it wouldn't actually work. But it just provides just enough so we can do some kind of animation like this. Now, something that's pretty difficult for people to get right is the intensity of the light sources, and also since we don't have a perfect 3D scene, the actual positions of the sources might not be the optimal positions to get realistic looking results. So we apply an optimization that tweaks the position a little bit, and also tries to estimate the intensity of these light sources, so that the rendered image, which is the one that we're looking at right now, so that it best matches the original input image. This is if we didn't tweak the lighting or use our optimization procedure. And then this is if once we apply the optimization, we get a much more realistic looking result. This is showing our technique for recovering external light sources. So we call these light shafts, and we just mean pools of light that are coming from outside the scene, and they're usually very strongly directed, such as sunlight or something like that. So what we first do is we have the user give kind of a mask of where the pools of light are. Then we know the direction in 3D where the sources are coming from, and then we use a shadow matting procedure, which tries to find shadows in the scene, and then we can use the opposite of that mask, or the unshadowed regions, and we call these. This is the pattern that we use for the light shafts. Using the window, we can figure out that the shaft should actually be rectangular and not this the strange pattern that we see on the floor from the occlusion. And then we can do a decent job of recovering what the shaft should look like, so when we insert an object, it looks decent.
So talk a little bit about where you're planning on going next with this. Obviously, this presentation is for SIGGRAPH coming up, right?
Mm-hmm. Right, so this will be presented at SIGGRAPH Asia in Hong Kong in a couple weeks. And so we have a bunch of ideas for future work. I mean, this could be extended to videos, which would be great. So that's one of the leading comments I've received so far from people who have watched the videos, that it's great that this works for single images, and a lot of people are really excited about it, but there's a whole other group of people that really want to see this working for videos. And so that's one of our main things that we're focusing on right now. We're actually working on an online demo right now so that everybody can try this out. it's still probably a couple months away from being finalized, but we think that it's pretty easy to use, and we think that everybody can should at least give it a try if they're interested in playing with it. And this all these results took about anywhere between 2 and 10 minutes to generate, not including render time. So the rendering takes quite a bit longer, but to actually generate the 3D scene and the animation, it's very quick.
Well, great. Thanks for taking the time to chat with me today, and good luck in Asia.
All right, thank you. Thanks for having me.
If you're interested in learning more about how difficult it can be to detect doctored digital photos, check out our August 2009 story, Seeing is Not Believing. Thanks for watching this episode of The Full Spectrum. I'm Josh Romero.